increasing fuel consumption and rising greenhouse gas emissions are forcing industries to improve the energy efficiency. Again, we are talking about sustainability and green energy. One way to achieve this, there are many ways in engineering to achieve sustainability and green energy or clean power, but in my research, one way to do this is to use the waste heat recovery system. That means the rejected heat, we have to recover it. We do this by collecting or charging or discharging latent heat energy storage using PCM. And PCM stands for phase change materials. The problem with the phase change materials is that they have low thermal conductivity. In general, when you want to have a good heat transfer, you have to have high thermal conductivity and you have to have big area for heat transfer. So the first problem with the phase change materials is that it has a very low thermal conductivity, and this is why we have to use nanoparticles to increase this thermal conductivity. Okay, so the aim of our study is, as I said before, we know that when you have high conductive materials, you have more heat transfer, and we also know when you have bigger area for heat transfer, you have better heat transfer. So here we use fins, and fins is nothing but extended surfaces. That means we want to increase the surface area for heat transfer. So we want to study we know that the fins will increase the heat transfer, but we want to know how would the fin shape affect this heat transfer, and also we want to know how would the orientation of the fin will affect the heat transfer. So mainly I'm talking about fin shape effect, and I'm talking about fin angle shift. Before that, let me give you a quick idea about what is the phase change material, PCM. Phase change material is a substance that can absorb and release heat. And you can think about it as like water, for example, it changes to ice, coconut, or even the wax of the candle. This is all examples of phase change materials. The most important thing of the phase change is that whenever I told you about heat transfer, definitely you think about temperature change, because this is what we know. If there is a temperature change, there is a heat transfer. But if you can see here, this is what's interesting about phase change. Here we have heat, because the heat is increasing this way, and the temperature is increasing that way. But while a material, while it's changing the phase, it's going to release heat without increasing the temperature, and this is the main point why we are using PCM, because they can release heat or absorb heat while they are preserving the temperature. Just a second, I would like to show you a short video about PCMs.
Into the fascinating world of phase change materials, or PCMs. Imagine a material that can store thermal energy just like a battery stores electrical energy. Sounds cool, right? That's exactly what PCMs do. When these materials melt or vaporize, they absorb heat. Later, when they cool down, they release that stored energy. So, how do engineers use this nifty trick? Well, PCMs are a game changer in various applications. Think about the thermal control of buildings. By integrating PCMs, we can maintain a stable indoor temperature, cutting down on heating and cooling costs. In photovoltaic plants, PCMs help manage the heat from solar panels, boosting efficiency. Ever wondered how hot and cold water storage systems stay at the right temperature? You guessed it, PCMs are at work here too. And let's not forget about the thermal management of electronic components. With PCMs, we can prevent overheating and ensure optimal performance. Now, let's talk materials. One of the most commonly used PCMs is paraffin wax. It's reliable and gets the job done, but that's not all. There are also hydrated salts, non-paraffin organics, and even metallic phase change materials. Each category has its own unique properties, making them suitable for different applications. In essence, PCMs are a powerful tool in an engineer's toolkit. They help us harness the physical phenomenon of phase transition to create more efficient, sustainable, and innovative solutions. So next time you're working on a project project that involves managing thermal energy. Remember the secret power of phase change materials? Until next time, keep innovating. Thanks for watching.
Okay, so the main point of the phase change material is that it can keep the temperature constant while it's absorbing or releasing heat. It depends on your application. So this is why it is called thermal batteries. So this is the case we are studying. We have this container, and I told you before that I want to study the fin shape effect. This is called T-fin shape, and we want to study the angular orientation. So we have 6 cases. The first 3 cases, it's the right angle, but we have different shape of the T. And for the other 3 cases, we have tilted angle of 45 degrees. So we want to know which shape is better and which orientation is better. So here we are looking at the temperature contours. As this is melting, that means we want everything to be yellow color. When it was cold, it was purple color. So if you compare case C1, C2, C3 at different times, and it's easy to look at 32 minutes. If you look at 32 minutes, it seems that this case, everything was melted, just maybe this is small zone. So from this picture, and from the other one where we have to see the melting fraction, as you can see here, everything in purple, that means it's not melted yet. Everything in brown, that means it's fully melted. And again, if you compare at 32 minutes, you could see that this is the best case because now everything was melted here and it's now liquid phase. So from here I can conclude that this shape is better than this two shapes. So now I know which shape is better, so I have to shift to the angle to see whether is this angle is better or 45 degrees better. When we come to the 45 degree, you will see again that this shape is better, but if you remember, if you compare this one to the right angle, there is some PCM here is not melted. And that means that 0 degree is better than the shifted is 45 degree. Again, here I will see the temperature with time, and this is for the first 3 cases. And if you remember that CC was the better, so around 30 or 25 minutes, everything was melted. But if you come here, I see in 25 minutes it's still going on. So again, the T shape was better, and the 0 angle was better. So as a quick conclusion, that we see that T-shaped fin in case 3 was better because it accelerates the melting and enhances the heat transfer rate. And when we have the tilted angle for cases 4, 5, and 6, this was worse because it's increased the melting time with 91%, 80%, and 65% respectively. So we concluded that case 3 with T-fin shape is better, and 0 degree is better than 45 degree. That's all, and thanks for your attention.
How much gases do you think this would help reduce?
Well, good question. Not too much. This is small scale. Yeah.
Since this is a very difficult question for me, I would like to ask you if you could give me some examples of practical application.
One example is for the PV cells. Yeah, so you know they need light, sunlight to generate electricity. The problem is when they have the sunlight, they also have heat, and when they heat up, the production of electricity goes down. So we have a big problem because we need the sun, and the sun has heat, and when the heats come, we have low production. So what we do is, on the bottom of the PV, we make a layer of the PCM. Why? Because it will keep the temperature, it will keep it cool. Because this PCM will absorb the heat that's coming from the sun to the PV cell. So this way we have longer time for good productivity. Another example for solar dividers. When you have solar divider, you know that you have sun, you can dry fruits, for example. Once it's sunset, you cannot because you don't have heat. Also, we can use the PCM because while the sun is producing the heat, the dryer can absorb just a fixed amount. So the rest of this amount can go and be stored in the PCM. Once the sun sets, it's cold. So now the PCM will start to heat the solar dryer. In this way, they extend some researchers extended the drying time about 3 or 4 hours more after sunset for free. Yeah.
That's nice.
Thank you.
Question, please. Thank you for your presentation, but I have a question about can we use this procedure in order to keep temperature for a long time and use it when we want
Yes, you are right. Yeah, it's 2 ways.
to it?
Yeah, you can heat or you can, yeah.
Yes, yes.
Yeah, exactly. So, and nowadays they use it also in the buildings. Yeah, for in summer and
Summer.
Yeah.